Hello and welcome back, everybody. Moving on to chapter 3. This chapter is the whole reason I decided to kind of write this text and make this series of videos. The title is Dynamics, and in particular dynamics in one dimension. For most of this semester, we'll be thinking about one-dimensional dynamics. Of course, we live in a three-dimensional world, and you can even add extra dimensions to that. So, future calculus courses, differential equations courses, etc. We'll get into higher dimensions, but we're going to work in one. Now, the reason why I wanted to kind of include a chapter on dynamics is that in reality, dynamics and its uses in the real world is the subject of calculus. This is actually why we study calculus. Because going back to really calculus 1, if we think about our two objects of calculus 1, differential and integral calculus, each of these objects, the derivative and the integral, they have like real life understandings, and the derivative is the slope of the tangent line. And the integral is it's the antiderivative, but it's also, when we maybe give it some definite bounds, a to b, this is the area under a curve from a to b. However, when we get to the real world, and I think a lot of you probably have been feeling this and maybe wonder why we're studying what we're studying, in the real world, we don't encounter these objects. We don't encounter slopes of tangent lines. It's a very abstract mathematical definition, right? To plot a specific curve and then calculate its slope, that's something that occurs basically mathematically. It occurs on paper. It doesn't occur in our daily lives. And similarly with areas under curves from A to B, if anybody ever asked you before you knew calculus how to calculate this or how to compute this, you would be able to do it. You could do this pretty darn well, not perfectly, but pretty darn well, without calculus. And even more so if I gave you a specific plot and I didn't even give you the function of the curve, right? To be able to use calculus on it, you would have to actually know what the function's equal to. But if I just gave you kind of a general curve with a general region and I didn't even give you a function for that, you wouldn't be able to use calculus to give yourself that area. But you would still do a pretty good job in real life. I mean, you would probably just, what they did in the past was get a piece of paper and cut it out with scissors and then weigh the piece of paper, and you get a pretty good approximation. And the real world operates under approximation. So in a lot of ways, the slopes of tangent lines, not really used in the real world. You're not, computing the difference of some function over a very short interval and then dividing it by the distance of that interval in your daily life very often. I mean, your speedometer does some version of approximates to that, but we have ways of doing both the derivative and the integral in approximations in real life that we didn't ever really need calculus for. So why do we study calculus so strongly? Why is it such an important topic that kind of everybody expects physicists, engineers, clearly mathematicians, statisticians, computer scientists to know really well? It's because of dynamics. Okay, so calculus is actually going to end up being a language in which we can predict the future. And so I'm going to give two new meanings to the derivative and the integral now for this section and really future sections as well. And I'm going to change my variable away from x, and I'm going to modify my new independent variable to be t. This will now be time for both my derivative and my integral. And when we think about the derivative from now on, d dt is going to reference a velocity, or really you should think of it as a trajectory. And you can think about the integral as a prediction about the future. Okay, because why is the derivative of velocity or trajectory? Well, we're calculating the change in an object over the change in time. That's the definition of a velocity. And in terms of trajectory, I mean to say, like, where is something headed? In what direction is it currently moving? And in the integral, we're talking about a prediction about the future, because what are we doing? We're going to undo a trajectory, or we're going to, if we think about what the integral actually does, right, this adds up many tiny changes. Right, the fundamental theorem says I'm going to undo the differential. So we're adding up many tiny changes. Over time, we're adding up many velocities or many trajectories. It's going to tell us where we exist in the future. If I add up my car's velocity as I've been driving from where I start and then a bunch of mini velocity changes, I'm going to be able to predict where I will be, right, if I just add a bunch of velocities together. And so that's what dynamics really is. Dynamics is the mathematics of predicting the future. And in particular, the derivative in dynamics land is a way that we can represent velocities or trajectories in some sort of abstract setting. You can talk about exponential growth rates, for example, as like the population of bacteria is growing, and that's like a trajectory of the bacteria is to get larger over time. And the integral really it undoes the derivative, so we can make predictions using the derivative, but then the integral actually solves our problem for us. And this is what calculus really does in the real world for us. It allows us to define situations. If we maybe know how velocities work in the real world, trajectories work in the real world, we can talk about situations in which velocities or trajectories are relevant. And then if we want to predict the future, we end up having to integrate those situations. Okay, so where do I get some examples of these dynamics? I've provided 3 examples before we really get into the meat and bones of the math, and these look very abstract for now. They feel very abstract. They will be very abstract. You have to take a few more math courses to understand any of these. We'll just start with the first one. You know, where do we actually predict the future in the real world? Well, you open up your phone, you ask what the weather is going to be tomorrow, and all of the scientists at NOAA are using the Navier-Stokes equations, as well as a lot of measurements of wind speed and pressure, etc., to predict the weather for you tomorrow. And these Navier-Stokes equations are a version of dynamics. In particular, what does the dynamics look like? Think about this weird looking DDT. This is still behaving like a derivative. This is technically called a partial derivative, but that just means that we live in a world with more than one dimension, and time is one of those dimensions. So you can take a derivative in time, but then you're equal to, you know, some other terms of derivatives in space is what we have there. And don't worry too much about what that's saying, but let's think about what's on the left here. This really is, it's a derivative in time of this object u. This object u technically is a velocity vector. So it's the change in velocity of a specific fluid. This is actually representing change in velocity. It's representing acceleration. And so the Navier-Stokes equations can tell us how the acceleration of a fluid depends on kind of how it's distributed over space. The equal sign, of course, means equals. So the velocity, change in velocity, is equal to how the fluid is distributed in space. And that's not really too surprising. You would expect if you have a high pressure system and a low pressure system near each other, then you're going to, you know, perform some sort of acceleration that's going to move the air from the high pressure system toward the low pressure system, or very similar situations. So we're not obviously going to be able to solve these equations today. You take more and more math courses for that. That's just one example of us using dynamics, using kind of a derivative in time to be able to predict the future. Right now we set up the equations, right? The scientists at NOAA, they set up the equations, but the equations themselves are not predictions of the future. You have to solve these equations with integrals to predict the future. Right, because the equations tell you how everything's related to each other, but you know, at the end of the day, what do I actually want? Is I want the kind of these velocity vectors as they evolve over time, and I'm going to have to integrate, or you know, in other words, actually solve the differential equation to be able to predict the future. So that's one example. We've got a second example, which is structural stress models, which is maybe how engineers would build bridges. Structural engineers, civil engineers, etc., would build bridges, and these stress models are based on the finite element method, where here we see our integral over here on the right hand side. We also see our summations, which we encountered in the last section. So we have some sort of integration and summation. The reason why we don't see derivatives here is that technically the finite element method has already solved a differential equation. So there's some differential equation lying underneath where this solution has been constructed out of, but that's just giving you another example of us using, you know, both integration and summation in the real world to kind of predict how a bridge might feel stress, for example. Or we've got something called the options contract prices, which here we have the Black-Scholes model. This is really a differential equation which predicts how we should price options contracts in the commodities market, so that, you know, basically nobody has arbitrage. And so, you know, financially, the entire financial system, at least in terms of investments, is based off of dynamics, right? So what this is saying is we're predicting the future value of a specific options contract, or we're currently calculating its trajectory, but its trajectory has to be equal to, you know, a lot of these other terms that we have here. And so we've got 3 examples of, you know, dynamics in the real world, or in some sense calculus in the real world, that's helping us predict the future. That's actually playing the role of why everybody wants you to learn calculus. It's not because you like to calculate areas. It's not because we like to know tangent lines. These things are not really used in the real world. If you're going to calculate areas, you're just going to do it numerically on a computer instead anyway, and I think all of you know that. So you've maybe been wondering why we are even studying what we're studying. This entire chapter is why. So let's get into the real section, which is continuous and discrete dynamics in one dimension. So this section, I'm not going to solve any dynamics. I'm just going to tell you what I mean when I use the word dynamics. Okay, and the point of dynamics is to predict the future, like I said before. Well, if we're going to be able to predict the future, we basically need to know 2 things. There's going to be 2 pieces of information that are incredibly important for predicting the future. The first piece of information is the current state of our world, or the current state of, a lot of times mathematicians and physicists will call this a system. Okay, so some current state of something that we're measuring. We've decided that we want to measure the height of a hot air balloon. Okay, we need to know where it starts. We need to know specifically, did this hot air balloon start on the ground? Did it start on top of a building? Did it start on top of a hill? Did it start in a valley? Did it start in a river? On top of a tree? Etc. We need to know where it started. And in fact, knowing where it started does include the past as well. So let's not forget that the past is important, even though a lot of times we only care about the present. And then we need to know rules, a collection of rules which are going to model causality. right? And these rules are basically going to transfer us from saying, hey, this is where my measurement stands currently, the current state of the world. But the rules are going to say, by the way, if we know the current state of the world, we can actually predict the future. But the rules are never going to be, they're easily stated in terms of derivatives usually. I'll say usually easy to state in terms of derivatives, because derivatives model how things change, right? That's the entire point of it. A derivative is that derivatives model change, and we know how to relate changes to one another. But what we want to do when we solve dynamics is actually get rid of the change. We want to know how something is, not how it changes, if that makes sense, right? Or in the future, we want to know what its value is, not how its value is going to change. We want a specific number, and so that's where the integral is going to come in later. But we need these two pieces of information, the current state of the world and rules which model causality. And now let's talk about how we would use mathematics, right? This is kind of going back to the language of mathematics, how to translate the English, which is, these two ideas of a current state and a rule. How do we translate that into something that can be described mathematically? Well, the following is how we do it. It's a little bit ugly, so we're going to talk our way through. What we have when we're talking about a dynamics is we have a function. And this function is going to do two things, right? It's going to interact with a position, which is the current state of the world or system. And it's going to interact with time windows, and this is going to be a window into the future. Okay, this function needs to interact with positions, which are the current state, as well as time windows, which are some, forward amount of time we're going to travel into the future. Now, my position for now, I'm going to label with the variable x, and the time window, I'm going to label with the interval t sub I comma t sub j. I'm using these subscripts just to denote two arbitrary times. Right, so there's just some window over which my function is going to interact. Well, this function needs to satisfy two properties. The first one, let's forget about. Let's look at this bottom one first. What does this function have to do when I'm interacting? Let's look at our time window here. Our time window starts at t0, and our time window ends at t0. Well, this is a time window of 0 width. Right, a time window, I'm talking about kind of evolving forward in time to the exact same point that I started, right? In some sense, the lower bound is like where I start, and the upper bound is where I end. Well, if I don't end anywhere different from where I start, how should my function, which describes the future, how should my function interact with the state of the world? Well, if I haven't evolved to the state of the world at all, I'm still standing where I started, the function better tell me I end up exactly where I start, because I am still where I start. I haven't moved anywhere in the future. Okay, very natural for this section. Let's see what the function's doing in this top part. So what's going on up here? Well, we have a composition going on. So I'm going to circle this one term here. This is an evolution. It's an evolution because I've taken my function and I've said I'm going to start at x, starting from x, well, that's very true, at time t0, and ending at time, what is the end of my time window here? It's t1, so some future time. Ending at time t1 in the future. Okay, so my function has to satisfy where that it evolves time a little bit. But what have I done is I've taken my entire function, which has evolved into the future up to time 1, and I've plugged in, or if you remember this word function composition, it's been composed into the position term of a second copy of f. Right, because there's a second copy of f on the outside here, and I've plugged that first copy of f into just the position term of that second copy. And then what am I doing with this outside copy of f is, well, I'm going to evolve it again. I'm going to start at t1, which is sometime in the future, right? It's where my first function ended. I'm starting at t1, and I'm going to evolve again up to t2. So now I've evolved, starting from t1 and ending at t2, a different time in the future. Well, let's think about it. If I have a specific measurement I take at the beginning of time, that's what x is referring to. I then start at t0, my initial time, and I move forward in time up to t1. But then my function turns around and says, oh, by the way, let's start at t1 and let's move towards t2. Well, if this is really predicting the future, what does my function have to do? It has to say that must have been the same as me starting from my initial point and just waiting the entire amount of time from t0 to t2. And so that's what this upper collection of far too many mathematical terms is actually trying to say. I mean, we do need this many mathematical terms, but what it's saying is that, hey, if my function can truly describe the future, it doesn't matter if I describe the future over one time interval and then over a second time interval, or if I describe the future all at once. Okay, and I do apologize if that's going over your head, but we're going to get into exercises, which makes this quite clearer. So this definition is quite abstract. That's what I say for the next thing. We apologize for including it initially in such an obtuse form. So I'm going to once again describe what's happening behind the scenes in this definition. That's what I've got here. So here I'm saying, suppose we have a rule system that we assume is true for describing causality. We're going to consider this rule system giving a name f. And f is going to input a position over the time window 0 to 0, a 0 amount of time window. And it's going to say, by the way, if I go a 0 amount of time window, I end where I started. That's going to mean, where do I stand right now? X is where I stand right now. Let's move forward 1 second into the future. This function f can predict where I exist 1 second in the future by saying, where am I right now and how long have I waited? Well, I've waited from the time window 0 to 1. And so it's going to output me somewhere. It's going to say, where do I stand 1 second in the future? We could also have asked the question instead, where do we expect to be 2 seconds in the future? And the only difference I'm going to say, instead of 1 second, where I put 1 there, is at 2 seconds, I'm going to put a 2 right there. And so I've got the function which predicts the future at time second 1, and the function that predicts the future at time second 2. But if the future is truly the future, I should have the ability to predict the future at time second 1, and then predict the future again over the interval 1 to 2. Right? This is 2 predictions lined up. Should still give me the same answer as a single prediction over the larger time window. If this is still not making sense, I would just pause the video and read it, because I do a pretty good job describing it in language. It's a hard concept, but it's just something that you have to pay enough attention to. We've got this statement here, and this is a restatement of what I had in the definition. And I just want to describe really what's going on if you don't even want to think about why this is working in terms of kind of metaphysically what I'm trying to say about all of these objects. You can think about it just as dynamics work if you look at this composition and I see T1 here and I see T1 here, and these can cancel. And my two F's absorb. So the two F's become one F, and the T1s that line up with each other can cancel. That's all it means to have a dynamics. So let's actually look at examples of this, because you may not believe me that these sorts of functions actually exist. You've been working with them your entire life, and you just haven't realized that. Anytime you've tried to predict the future with math, which does happen, right? You're already looking at what's on the screen. It says exponential growth. So it does happen that we can predict the future with math all the time. You just probably didn't realize that what you were doing was dynamics. So we're going to show that this works. When it comes to exponential growth, let's say particularly with bacteria, the natural function you probably all memorized was, well, the population at some future time t is equal to the current population, and then multiplied by e to the rt, some exponential rate, r times time t. And so if we happen to have something like, how much bacteria do we have in 3 hours? We just plug in a 3 for time and we get our answer. Well, it may not seem so, but actually our predicted population, meaning what's on the left here, what we're trying to predict, is a function of time windows and initial populations, the thing we're measuring. We should always think about this spatial variable or the position variable as whatever we decide to measure in our experiment. And so we are actually a function of time windows here and some other variable p0. And so we can think about this p, the population p, as a function of two variables. This is my position variable, and then this is my time window. And where does it map the initial position variable? Well, it just puts it at p0. Where does the time window end up? Well, it just ends up at t minus t0, right? Up here, there's really a hidden 0 sitting in there saying I'm starting from time 0. You can imagine if I were asking the question about how much has the bacteria grown since 1 p.m. and it's actually 8 p.m. now. You can't actually just plug 8 p.m. into it. You have to plug 8 minus 1 p.m. into it to get 7. You need kind of the total evolution of time. So that's why it's going to be t minus t0 and not just t in the power. And so we have a function of some sort of initial position or initial population and of a time window. And we can actually see that the definition of a dynamics is satisfied for this particular function. Now, what do I have to do with this function to show that I satisfy a dynamics is I need to verify that, well, first of all, if I compose these functions, then time windows add, right? Time windows add together. And secondarily, I have to show that the function over a trivial or 0 time window reproduces its input. Right? If I'm truly predicting the future, if I don't wait any amount of time, then I should be where I was already standing, or I should measure what I've already measured. So we got to satisfy those two things. Let's verify the first. So to verify the first, we're going to compose a function with itself and see if the time windows happen to add together. What do I mean by compose it with itself? Well, I'm going to take this function. There it is, right? So that's me just grabbing the function itself. But I've plugged it into a second version of itself. So there it is sitting inside of the second version of itself. It's taking the place of the position variable, just p0. So I plugged it in for p0 in a second version of itself. And to make sure that the time windows add, I have to make sure I use the same variable on both time windows. So the last variable in the first time window is the first time variable in the second time window. If I go through this work and I actually calculate what this composition of functions looks like, this is why we study function composition. So if I look at what the function compositions look like, well, what do I have to do with this term that I have in for p0? Well, since I'm composing it for p0, that means it takes the place of p0 in the equation. And so this entire term is taking place of p0. And then what's left over, what's this e to the r t minus t0 going to be? Well, it's e to the r. I've written t2 minus t1. Why have I written t2 minus t1? Well, it's because the time window is the window t1 to t2. So when the time window is t1 to t2, that extra exponential power is going to be e to the r t2 minus t1. At this point, I just have to simplify. Now simplify. And when I simplify, I can use my exponential rules. There's a multiplication of exponentials, which means I'm going to add the powers together. When I add the powers together, we see a positive RT1 and a negative RT1. So those cancel. And if I just factor the R out of these two remaining terms, I get P0 e to the R T2 minus T0. Let's think about what that actually is in terms of our original dynamics. Well, the T0 is still there in our original dynamics, but my upper bound of my time window is T2, so that's going to be a T2 on the left-hand side here. So it's really P of P0, comma, the interval T0 to T2. And that's what I've put at the bottom. And now, what have I just shown? I've shown that I can add time windows together, right? Because my time windows on the left here, T0 to T1, got added to the time window T1 to T2, and I've just gained the time window T0 to T2. Think about it in terms of intervals. If this is T0 to T1, and secondarily I've got the interval T1 to T2, then if I compose my functions, I'm just adding these two intervals together to get the full interval T0 to T2. So that's the first of the two identities I have to show is true for me to verify that this is a dynamics. And then the second identity is to show that, hey, if my time window is degenerate, or it's a length of 0 interval, then I should just start. I should end up where I start because I haven't moved at all. So let's verify that that's true. If I'm plugging in T0 for the second bound in my time window, that's me putting a T0 right there. So we see that the power in the exponential happens to be a power 0, but a power 0 is going to make that exponential equal to 1, and I'm just going to be left with P0, my initial population. And so we see that this expression, or this function of an initial population P0 and a time window satisfies both properties of dynamics. We can say this is actually going to predict the future for us. So that's really nice that we can mathematically verify that something has the ability to predict the future for us. It's really quite useful. Got another lovely example here, and that's really what we're going to be encountering today, is just so many examples of predicting the future in useful ways. Got falling objects. And if you took a calculus-based physics course, you would probably have derived this yourself. We don't have physics in this class necessarily as a prereq, so I won't be going through the derivation of the following, but if you decide to drop an object maybe off the side of a building, you can calculate its position. Now we use s as the position, which is very interesting. It comes from Latin, meaning like statum, I believe, or the status of something. It means the place of something. So the position that we're going to predict of my falling object thrown off the side of a building or something over time is going to be, well, negative g, that's gravity acting to pull things down. That's why it's negative. T squared over 2, that's going to come from actually integrating a constant twice, is where it comes from. And then we have some initial velocity, depending on if I throw it upwards or downwards from the beginning over time, because velocity moves things proportional to the amount of time that you've waited. And finally, we have its initial position, s is 0. So that's really what this function is talking about. And it does satisfy the definition of dynamics, but it satisfies the definition of a two-dimensional dynamics. If you ever study what are called Hamiltonian systems, that's what this actually satisfies. It's not what we're studying today. We're just studying one-dimensional dynamics. And so we're going to go ahead and take a derivative of this function. We're going to end up with a function of velocity over time. So s prime, also known as v for velocity, it's going to be the derivative of this object over time. It's going to be negative gravity times time plus my initial velocity. And I am claiming that the equation which models how the velocity evolves over time satisfies a one-dimensional continuous dynamics. Let's actually see this happen. It's going to happen by me interpreting this equation of velocity v of t really as a function of time windows. So I'll say t0 up to t, there's my time window, as well as its initial condition, which is v0. Okay, so I'm going to reinterpret it as a function of both time windows and initial velocity. And when I do that, what it actually looks like is going to be negative g times the length of the time window plus the initial velocity. And I'm claiming that this satisfies the definition of dynamics. It's valid to predict the future, but I have to show that that's true by showing the two things I was showing earlier. I have to show first that if I compose these, then I can add the time windows together. And two, if I have a degenerate time window, or 0 time window of length 0, I haven't changed at all. Well, to do one, let's go ahead and compose. So I have to grab this, I'm going to plug it into itself, right? So there it's been plugged into itself just for the term v0 inside of itself, right? So wherever v0 shows up, I'm going to plug it into itself. And now this composition says, well, where does v0 end up? It ends up as this additive term. And so that's why I've included the entire definition of my dynamics in for v0 over the time window t0 to t1. And so that's why I've got t1 minus t0 here. So that's kind of the inner composition term. Just this part ended up right there. And then my outside composition term, this v of t1, t2, that's going to give me this negative g of t2 minus t1 on the outside. And so now all I have to do is simplify. And we see that if I simplify everything here, what do I have? I end up with a positive gt1, I end up with a negative gt1, so those both cancel. And if I factor out the g's from my negative t2 and my positive t0, I'm going to end up with negative g t2 minus t0, and there's a single v0 that's coming along for the ride that's going to end up at the end. Well, what do I actually have here at the very end? If I make my life a little clearer, what did I just construct? Well, that happens to be my original function, but over a larger time window, right? My time window here is now t2 to t0. T0 to T2 time window. And so I was able to add the time windows together, in some sense cancel the T1s out of it, and just end up with a larger time window here. That's the first of the two identities I have to satisfy. And then the second identity says, let's plug in a degenerate time interval. So plugging in T0 for both entries, that's plugging in T0 for both entries on the right-hand side. What that's going to give me is negative g times 0 plus the initial velocity, which means I only end up at the initial velocity. It means I haven't changed at all in time. And so I satisfy both definitions of the dynamics, which means that this is perfectly valid to predict the future with. Okay, so those last two cases were the cases of continuous dynamics, right? And we have already encountered in this class that there's a continuous calculus, and it's kind of the one that we like to learn. It's the one that gives us tangent lines, gives us integrals. There's also a discrete calculus, and some events in the real world happen in discrete steps, you know, daily high temperatures, basketball shots during a basketball game, amount of people in a specific grocery store clerk's line, you know, and even the number of groceries on the specific belt, right? These are all discrete steps. So you can't have, you know, 1/2 of an item of groceries. And so because of this, we also have discrete dynamics. And really everything behaves the same for discrete dynamics, right? Nothing should look different. We just have to understand that rather than time evolving continuously, time is allowed to evolve in discrete steps. So it's able to jump bing, 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 rather than ooh. That's kind of the difference between discrete and continuous, I would say. So yeah, we've got the same sort of definition of dynamics, but now we've got it for discrete, where now I'm looking at my time windows being subsets of the integers, and I've used that double bracket notation to describe these intervals of integers instead, but everything else looks the same, right? I still have this notion of time windows adding together, and my functions absorb. And if I look at the function over a degenerate time window, then I don't move at all. So everything stays the same. We're just thinking about now we have the ability to work in discrete steps instead. So let's look at a couple examples of these in discrete time. And a classic example, it's probably going to be quite pertinent to anyone watching this, is the accrual of student loan debt. Right? We already experienced exponential growth with the population of bacteria in the previous section. But in this section now we're talking about accrual of student loan debt. Student loan debt's only going to accrue in discrete time steps, right? Because it gets compounded monthly usually, right? You're going to make a new payment every month, but you also get a new notification of how much you owe every month. And so the equation, which models the debt D over however many months we've moved forward, N, the number of months, is given by the principal. It's usually denoted as A0, or the initial loan amount. And then we have 1 plus R, so that's 1 plus your annual percent rate, to the power N over 12, right? Where N is the number of months we've waited. And that's just going to determine how much debt we owe, right? Because N can only be discrete numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and future years as well. This is going to be a discrete dynamics. But let's think about why this is a discrete dynamics. We're going to do the same thing we've been doing before, and we have to make sure that we're talking about our equation, or our function D, as a function of two variables. It's a function of the initial debt, as well as a function of how long we've had debt. And how does that function really work? Well, the initial debt shows up at the beginning, and then the total length of the debt that you've had shows up in the power. And we should show that this actually can predict the future for us. Well, to show that it actually can predict the future, we need to satisfy our two steps of dynamics, that if we compose the function with itself, and then the time windows add, and 2, if we evaluate over a degenerate time window, nothing changes. So let's actually do this here. To compose, I have to grab my function and I have to plug it in. I'll have to plug it in for this value A0, right? It's its new loan amount. The debt has changed if I'm plugging it into itself. So there I've gone ahead and plugged it into itself, and then I've considered my initial time window and my second time window there. And if I actually write out what they all are, well, I have to really plug this entire term in for A0, and so that's me plugging the entire term in for A0, and then what's left over occurs over this time window N1 to N2, and so there it is occurring over the time window N1 to N2, and now I simply have to simplify. Well, I've got my 1 plus R terms, and both 1 plus R terms are exponentials of the same base, so I can add their exponents, and what we see is we have a positive n1 over 12 and we have a negative n1 over 12. Those two n1s are going to cancel. What we're going to be left with is n2 minus n0 over 12. And if we think about what this equation actually is that this equation is just the debt over the larger time window, n0 to n2. Then to prove the second part, we just want to show that if I plug in a degenerate time window, or time window of length 0, meaning n0 for both cases, that my power ends up being n0 minus n0, or a power of 0, which means that my debt hasn't changed at all. Right? If I haven't waited any months since I took on the debt, it shouldn't have changed at all. And so there you go. You can see that this satisfies the definition of a discrete dynamics. Okay, and then our last example for today is called the extraction efficiency equation. And it's for any of you that are interested in chemistry. There's this thing called extraction, idea called extraction. You use it a lot in organic chemistry if you happen to use some aqueous solvents and reagents to actually produce an organic molecule, but you eventually want to purify it. What you do is you've got a beaker with some aqueous liquid in it and a lot of your product that you would like to extract, and you end up adding a nonpolar solvent. So I'll make the nonpolar solvent orange here. So you pour that nonpolar solvent in there and mix it up, and what happens is that a lot of these organic particles that you've just created end up migrating into the nonpolar liquid, and then you allow the liquids to separate and you decant one off of the other, or maybe you extract it with an extraction funnel instead. And then you can repeat the process. Okay, so if you repeat the process, then you get more extracted in the second run, you repeat it, you get more extracted in the third run, and so on. Well, it turns out, I've got a lot of equations sitting around here. If you care about the concentration of the solute that's specifically in the aqueous section, the aqueous phase, then the equation that you get out of it is what I have at the bottom. And so it depends on the initial concentration of the solute, as well as the total number of washing steps you've performed, or extraction steps. Number of extraction steps. We sometimes call those washes. And the equation just looks like, well, you have a volume of an aqueous amount of solvent, you have a volume of organic solvent, and then you have this D, which is called the distribution ratio, which you can see at the top. It doesn't really matter, but what does matter is that this time window shows up in the power right there, n minus n0, and your initial concentration shows up as a multiplier. And so we can show that actually this is a dynamics, meaning we can predict how much concentration we'll have after a specific amount of washes. We should show that it's a dynamics by actually, computing the two things we've been computing all day, which is to say I'm going to plug one version of this function inside of a second version of the function and see if the time windows add. Okay, so there's my first time window, n0 to n1, my second time window, n1 to n2, and I've plugged the first case in for the kind of the initial value inside the second case. And so this initial value term has been plugged in for the initial value all the way on the right, and then my second case of the function is sitting around up here, and now my job is to simplify. In this case, if I simplify, as always, I've got two exponentials of the same base, so I can add the powers n2 minus n1 and n1 minus n0 together, and it turns out the n1s are going to cancel, and I'm going to be left with n2 minus n0, which, by the way, is the same as if I had just moved an n0 over n2 time window from the beginning. So that's behaving the same as always, and we can also verify that, hey, if I don't perform any washes, meaning the number of washes that I start is the number of washes that I end on, and I just look at that, then yeah, my total concentration at the end, because this power is a power 0, the entire term up here becomes 1, the concentration at the end is the concentration that I started with, right? If I'm not actually going to perform any of these washes, my concentration shouldn't have changed. And so, yeah, you can apply this to chemistry as well, student loan debt. You saw, physics with gravity, making objects fall, biology, basically anything in STEM, anytime we're trying to predict the future, it's going to be a dynamics. And we can mathematically verify that our functions are at least able to predict the future. They may not do a good job modeling specifically what we're trying to get them to model, but they do at least verify kind of our intuitions about how the future must behave with these functions. Anyway, that's all I've got. I know it was a long one, very conceptual as well. Thanks for hanging in there. I'll see you in the next one. Bye.